Hi everybody, we're going to talk about heat of vaporization today. So remember that we are talking about solids or liquids, which are condensed states of matter, and so because the particles are so close to each other, the intermolecular forces are significant. And those intermolecular forces affect all kinds of different properties. We've already talked about melting points and boiling points and solubility being affected by intermolecular forces. So another property that's affected by intermolecular forces is heat of vaporization. So if we look at the vaporization, if you have a liquid and you're turning into a gas, you need to add heat. So heat is absorbed by that liquid in order to turn into a gas. And so that process is endothermic. And the molar heat of vaporization is the amount of heat that would be absorbed when 1 mole of your substance turns into vapor. So heat absorbed to vaporize 1 mole of liquid. So if you think about this, you're turning a liquid into a gas, so you're separating those particles physically, spreading them more apart, and so heat is required. And so if the particles are really attracted to each other, it's going to be more difficult to get them to turn into a gas, and it's going to require more energy or more heat. So the stronger the intermolecular forces, the higher the heat of vaporization. And again, this is an endothermic process. Remember, that's how sweat cools your body. So when you sweat, it's a liquid sitting on your skin. And so in order for that liquid to vaporize, turn into gas, it needs to absorb some heat. So where is it going to absorb the heat from your body? And so it takes away the heat from your body in order for the sweat to evaporate, and it leaves your body cooler. Similar to heat of vaporization is heat of condensation. So heat of condensation is how much heat is transferred when you take a mole of gas and turn it into a liquid. And so because gases are higher in potential energy than liquids, in order to go from a gas to a liquid, it has to release some energy. And so this process is exothermic. And the molar heat of condensation is the heat that is released to condense 1 mole of gas to turn it into a liquid. The heat of vaporization and the heat of condensation for the same substance should be exactly the same number. The only difference is the sign here. So condensation is exothermic. If you remember in honors chem, one of the extra credit questions on one of the tests that we had was, in Florida, when it gets a little bit cold, the farmers will spray the oranges with water to prevent them from freezing. And I asked you to explain it. And so the reason is when you spray the oranges with water and it gets cold, as the water freezes, turns into solid, it's going to release some heat. And so some of that heat will go into the oranges to keep them warm. So our classic question that we saw last year, which burns you more, water at 100 Celsius or water vapor at 100 Celsius, and why? So we know it's water vapor. And so what is the reason? Well, the reason is because it has more potential energy. And so both of them will burn you because of the difference between their temperature and your temperature. Body temperature is like 37 Celsius. So because they're at a higher temperature, they're going to transfer heat to your hand. So both of them are going to burn you, but water vapor will burn you more because it's going to transfer heat to your body to cool down, to lower its temperature, right, to match your temperature, but also because it's going to, in addition, condense as well on your body. And so when it condenses, it releases heat. So the gas particles condense releasing more energy. to your hand. And this is in addition to the energy released because of the difference in temperature. So it's releasing energy to your hand in two ways, or for two reasons. One, because of the difference in temperature, and then also as it condenses. Okay, so a little flashback from chapter 5. Remember, this is a heating curve. Can have a cooling curve as well. This is for water. So it says 1 liter of water at 25 Celsius is heated. How much heat energy is absorbed in order to vaporize the water? And they give us the density of the water at that temperature. So remember that we are taking a couple of steps here. So we are going from 25 Celsius to somewhere here. We're taking that liquid at 25, and then we're going to turn it into liquid at 100, so we're going to increase its temperature. So that's an MC delta T. And then we're going to go from here, where the liquid is at 100 Celsius, to vaporize it, to turn it into a gas at 100 Celsius. And this is the Q equals, oops, sorry about that, Q equals ml. So 2 steps here, but both of them require us to know what the mass is. And we're not given the mass, we're just given the volume, but we are given the density as well. So let's find the mass. So we have 1 liter of water. Let's change the liters to milliliters. And then 1 milliliter is the same thing as cubic centimeter. And the reason why I'm converting that is because this is in cubic centimeters, grams per cubic centimeters. Or if you convert this to grams per milliliters, which is would be the same, 0.997, then you wouldn't have to do this step. Anyway, so I'm going to put cubic centimeters here so they cancel, grams here, and it's 0.997 grams per centimeters cubed. So 0.997 grams per 1 centimeter cubed. And so this gives you 997 grams. So now I'm going to list my steps. So I'm going to take my liquid from 25 Celsius to 100 Celsius. And then I'm going to take my liquid at 100 Celsius to turn it into a gas at 100 Celsius. So for this step, I'm going to use Q equals MC delta T like we said. So Q is going to be the mass, which is 997 grams. C is 4.184 joules per gram Celsius. And delta T, to go from 25 to 100, you do 100 minus 25, final minus initial, so 75 Celsius. And then we're going to add to that Q equals ml, so the mass is 997 grams. Now, the heat of vaporization here, they're always going to give it to you. You don't need to memorize it. Before, we had it in kilojoules or joules per gram. Now it's given to us per mole, which is not a problem. We just need to do an extra step where we change this to moles first. So it's water, so 1 mole is 18 grams. And then we want to get rid of the moles, so we're going to put it here. We want the amount of heat, so kilojoules, and it's 40.7 kilojoules per mole. The only problem with adding those is this is going to end up giving you kilojoules, whereas this one, your grams cancel, your Celsius cancel, you're going to end up with joules. So this is joules and kilojoules. We can't do that, so we have to convert one of them. It doesn't really matter which one you convert. I'll just go ahead and say 1 kilojoule is 1,000 joules. That way, both of these give me joules and I can add them up. And so it actually ends up being a really big number at the end. Maybe we should have converted it to kilojoules. So that ends up being 2,600 kilojoules. Okay, let's look at the next one. It says the enthalpy of formation of ethanol is given to us, and the enthalpy of formation of ethanol, so this is ethanol liquid, and this is ethanol gas, and we have the heat of formation for both of them. We want to find the heat of vaporization. So let's think about this. They want the heat of vaporization. In order to vaporize something, you're going from liquid to gas. So you're taking your ethanol liquid and you're turning into ethanol gas. Basically, we want to find the delta H of vaporization, which is the delta H for this process right here. And they give us heats of formation. Now remember, when we want to find something with heats of formation, we say the equation for heats of formation is delta H of the reaction is equal to the heats of formation of the products minus the heats of formation of the reactants. So if we want to find delta H for this reaction, and we're given the heats of formation of reactants and products, that's pretty easy, right? It's just, thinking about what to do is the hard part in chemistry. So this is the delta H of vaporization, because that's my reaction here. My product is the gas, and so the heat of formation of the gas is negative 235.1 kilojoules per mole, minus, and then my reactant is the liquid. It is negative 277.7 kilojoules per mole. And so at the end we get, looks like this number is bigger, so it's going to be a positive value, and it's 42.6 kilojoules per mole. Does that make sense that it's an endothermic process? Yes, it does, because we're vaporizing. So in order to take a liquid to turn it into a gas, we have to put in energy, so it makes sense that that's positive. Always make sure that your answers make sense. All right, last part here. We want to rank the following in order of increasing heat of vaporization. So let's think about this. Heat of vaporization is affected by intermolecular forces. So what we want to do is draw these out and see what type of intermolecular forces they have. So let's go ahead and draw these. So acetone, you have a carbon with a double bond O, and then there's a CH3 here, and another CH3 there. I've got two pairs of lone pairs here. Butane, bunch of 4 carbons, and then you have a bunch of hydrogens. Acetone is sometimes added to nail polish remover. Butane is lighter fluid. Water, obviously, you know that one. And then ethanol, it's a type of alcohol. It's used as a cleaner. It's used as a fuel. It's used in alcoholic drinks. All kinds of uses for ethanol here. So after we draw them, we want to assign what type of intermolecular forces they have. So this has dipole interactions, and of course London dispersion as well. All of them have London dispersion, right? This one only has London dispersion because it's nonpolar. This one has hydrogen bonding, and of course dipole and London dispersion. We're listing the strongest type of intermolecular force in order to rank them. And then this one also has hydrogen bonding. And we're going from in order of increasing heat of vaporization, so lowest to highest. So remember, the stronger the intermolecular forces, the higher the heat of vaporization. So if we want to go from lowest heat of vaporization to highest, we want to go from weakest intermolecular forces to strongest. So out of these, the weakest would be butane. So this is number 1, lowest heat of vaporization. Then we're going to go to our dipole, number 2. And then between our hydrogen bonding, remember we talked about this, that water has more sites for hydrogen bonding, because all over the molecule you have partial positives and negatives that attract other water particles. With ethanol, you only have right here, these are the only sites for hydrogen bonding. So most of your molecule does not have sites for hydrogen bonding, and so the hydrogen bonding here is stronger than in the ethanol. And so this would be number 3. This one's number 4. This would be the highest delta H of vaporization.